Hi everyone, thanks for joining. We'll be live we will start the presentation in 5 more minutes. Let's wait for everybody to join. Hi everyone, welcome to the first live Carbon Byte Night of 2020 from Young Energy Performance Group. It's our first event hosted online, so please excuse us if there's any technical problem. We hope not. And yeah, wait just a second. And you can see our team here. We're a big team. And I will not go through all of the names of the group. You can be also one of them, but I would like to give a special thanks to Rosella supporting. She's our chairman, supporting all the events and everything, and being in the forward always. And she's the one leading the group and making everything possible. Then, okay, I would like to mention something first. So please make sure that you have joined the event with your email if you want to get a CPD afterwards. We can get the records in the end of the event and then send you a CPD in your email. If you have joined as anonymous from the web, we will not be able to get your details. So please, if you're anonymous, then rejoin the event with your personal email. Thank you. And moving forward, we are already 100 attendees. That's good. I would like to give a special thanks also to the team organizing this event, Tom Barton, Ryan Harris, and Harry Day. And then also a special thanks to Rosin Sweeney from CIBSE that she helped hosting the events on Microsoft Teams, and Costas from our part that helped us with the technical parts of hosting the live event. And I will introduce our speakers later on. Our mission of the YEPG is to promote discussions and that lead to new ideas and help the sector move forward. And this is it's a place for all young professionals, and it's promoting networking and collaboration, and you can be part of this. It's a place where we're discussing and making it possible to move forward, and it's where it can lead to your professional development. Some of our events, what we are doing, we're taking part in conferences. We have building tours, not only building tours. It can be an energy center. It can be a building with exceptional building services. It can be social, it can be quiz nights, or it can be another social event just to make the group more attached together and have a special connection to each other. That's how we can organize everything better and make everything running. And if you want to be part of the group, there is on 6th of May, there is the annual meeting where you can come and become part of the groups. It will be hosted on Teams online due to the current situation, and then you can go on our Twitter page for more details and how to join. And our agenda for today, Gerald Bruce will introduce the 5th generation district heating, its benefits and key issues. The considerations for 4th and 5th generation communal heat networks will be described by Tom Newton from Fairheat, and available technologies, implementation and case studies will be from Chris Davison from Genius Energy Labs. I won't keep much of the time. I will let the speakers talk. Bruce, if you could tell, Bruce from WSP, if you could tell some things for yourself and start with the 5th generation district heating. Just to mention, there will be a question section in the end of the event, so you can keep posting questions and we will select the ones that we can answer, and we will transfer them to the end of the meeting, in the end of the event, so that we can have. Unfortunately, we cannot have a conversation as we usually do in our events, instead of just questions and answers. But we hope to get most of your questions and create a good environment.
Okay, thank you, Nikos. Hopefully you can see my presentation. Is that up there?
Yes.
Okay, thank you. Right, as Nikos has said, my name is Bruce Geldard. I'm a technical director with the WSP Energy Solutions team. I can't claim to meet the young profile associated with this group, so thank you very much for allowing me to come and talk to you this evening. I've been working in district energy for about 2.5 decades now. My first scheme was a gas CHP scheme on the Isle of Dogs in London back in the late 90s, and it's been a pleasure to see the industry developing through time, and particularly to see these new developments, as we're going to be talking about this evening, taking us on to the 5th generation of district energy schemes. So Nikos has already introduced the title, so I'll go into what I'll be talking about. I'm going to start off just with a quick, what do we mean by 5th generation? I think everybody would be surprised to know that there have been generations 1 to 4. So I'll be talking about that, what we mean by that, and also, spoiler alert, it's probably not just 4th generation plus. I'll be talking about some of the key benefits and also some of the issues that we need to address before we start taking these projects forward in a meaningful way. So, how does 5th generation relate to other generations? Many of you might be quite surprised to know that district heating started its life back in the 19th century with steam systems, which didn't call themselves the 1st generation at that time, but we now think of them as the precursors of all the district energy schemes that we're talking about now. These were mainly served by steam from coal. They ran very hot. And through time, those temperatures have gradually come down and the sources of energy have changed. So you'll see 2nd generation being high temperature hot water. So that's highly pressurized, still running in ducts in the ground, in the sort of 120 to 150 degrees C range. An example of that would be the scheme that sits underneath Whitehall. The Whitehall district heating scheme was originally designed as a 130 degree system running high pressure hot water. They have gradually tried to bring that down. The other schemes that might be familiar, in Battersea there was a scheme running off a coal-fired power station across the river. In Pimlico, sorry, there was a coal-fired CHP scheme back in the 1950s running from the Battersea power station. So that would have been a 2nd generation. 3rd generation was really where I started to come into the industry. Medium temperature hot water, something below 100 degrees. We used to quite frequently be running at 90, 95 degrees. It was typically fired from gas or oil CHP with some energy from waste schemes in there. It was when pre-insulated pipes started to be introduced, and that involved burying those pipes directly in the ground and increased the performance of the systems markedly. Now, more recently, in the 21st century, we have been gradually reducing those temperature over time, and we now think of a 4th generation system serving well-designed modern buildings with low temperature internal heating systems with flow temperatures in the range of 50 to 70 degrees centigrade, and those can start using some of the higher temperature renewable sources, probably using plastic pipework because it's cheaper and it's not challenged as much by the sorts of temperatures we're talking about. But when we get into 5th generation, we're really talking about a change of concept. Yes, it is a lower temperature, and as you can see from those little graphs, the temperature's coming down, the carbon performance is going up. And by that I mean our improvement in carbon emission reductions over whatever your alternative might be. But the 5th generation is really using what you might call ambient water, probably uninsulated, and can provide heating and cooling. I'll talk about that a bit more in a minute. But I think the important thing to note is that those first 4 generations all were based on a central heat production and effectively passive buildings. So you were passing heat over into the building. They didn't have to do anything with it. They just used it within their own systems. As for the 5th generation, that is really a much more passive production. You're really circulating heat which is being produced elsewhere, and you're using that actively within a building. And I'll talk about that as we go through into the technical features of these systems. So the first thing we've talked about is very low temperature. Now there are 2 main areas you could talk about in terms of those temperatures. One would be ambient, in the kind of normal 10 to 20 degrees centigrade. So you might be talking about taking water out of a lake or the sea. You might be talking about a ground loop. The other type of system you'd be talking about would be recovered heat. That might be heat you're recovering from a data center cooling or similar. And it's in there that you get to see that you could actually start to think about a heating and cooling system, taking heat out at 20 or 40 degrees and maybe rejecting it in at 20 to 40 degrees as well. Now, because those systems are of such low temperature, you could be using uninsulated plastic pipework. That's the sort of MDPE pipework pictured there on the right. Now, you can be doing that at quite large scale. If you think about big water or gas pipes in the ground, it's quite a lot cheaper to install, and it's also more easy to handle than the sort of standard pre-insulated steel pipework that you might be looking at in district energy normally. If you're looking at some of the recovered heat systems with the higher flow temperatures, just to make sure that you do maintain the excellent performance, you may look at insulating your flow pipework, but you'd very rarely be insulating your return pipework. And that's all based on the idea that these systems are buried underground. If you come above ground, you probably will be wanting to insulate. Now, the reason why you can provide heating or cooling is because, as I've said, the building takes an active role in how this heat is used. The building takes or injects heat via a heat pump. Those are a fairly large set of heat pumps from Star. Now, that would be sitting at the very large end of the system. Those can also be individual houses taking heat via a little shoebox heat pump or similar, something that would just sit in your boiler cupboard. One of the important points about that is that those heat pumps can be selected to suit whatever the building system is. So you can have the temperature match between what your heat pump is outputting and your building requires. That's important for a few reasons, and not the least one of which is a commercial consideration, which I'll talk about in a sec. So overall, we're talking about a very different system than a standard district heating scheme. So these are some of the typical commercial features. My focus in life at the moment tends to be around the commercial, and I'm thinking very much about how you get to persuade end users to sign up to a district energy scheme. And these are some of the things which are quite important in relation to alternatives, this as an alternative to a standard district energy scheme. The largest cost item in the system is quite often, in this case, not going to be the pipework under the ground, but it's going to be the heat pump. And that's probably going to be owned by the building. It may be financed in some other way, but typically the building owner is going to take charge of that. It can be maintained by the energy services company that's providing the district heating system, but it really belongs to the building. It's part of the building's overall system. That means that the building owner can, on an individual basis, assess whether it's worth improving the coefficient of performance of that heat pump, or whether it's by changing the building systems to reduce flow temperatures. most buildings, as they, in terms of a retrofit, would be designed with relatively high flow temperatures, and that would have an impact on the heat pump performance and therefore the life cost of that system. So the building owner can look at that on their own merits and take into account their own considerations when looking at the value, the relative value of those investments. Typically, a customer might pay a facility fee or a standing charge only. Now, there will be circumstances when somebody needs to be paying for some energy as well, or a portion of energy would need to be paid for, where the system isn't perfectly balanced or there isn't an endless supply of energy. And I'll talk about some of the potential sources a bit later. But the facility fee would be there to replicate what you might see if you were, for example, a building wanting to use a ground source heat pump or to abstract water from a stream. So instead of paying a capital charge, you pay an annual fee for the facility that is being provided to you. That means that the metering of energy is basically on electricity. Now, that's obviously a lot easier than metering heat, and the customer gets to pay their own electricity company for the units, and therefore they can go out to market competition in the same way. Those are quite important features of this, which are very different from a district energy scheme where you're asking somebody to pay based on a relatively complex heat meter, and to pay the district energy company as well as paying unit charges to their electricity company. There are lots of different variations of the ways these things can be put together. Those are just some typical examples of the way in which this might be paid for. You can get a balanced system. Now, this is the sort of system you might get in a compact city area where you've got people who are trying to reject heat. In here, we've got an ice rink and some different computer systems and so on. But equally, you might have people wanting heat and hot water. So you can all be putting energy in and out of this system, paying the facility charge for that purpose. And you'll see this system has a ground coupling loop, which would be acting as a balancing area, a balancing line to make sure that the energy within the system remained balanced. You're looking to match that heating and cooling load. There is a way of pushing energy into and out of a store over time. It's most likely to be in a dense area, but it may need top up from a central system, particularly when it's trying to find that balance initially. Two other main systems are really where you've got an ambient resource, which can, for the purposes of the scheme you're looking at, be considered to be infinite. So you might consider the amount taking energy out of a river, out of the lake or a sea, or even mine water. Now, what you're doing there is you're matching your source and your off-takers in a much more traditional way. The resource is being replenished from the environment, so rivers and lakes are being warmed by the sea, the mine water is being warmed by geological processes. And the size of the extract is there to match up with the demand you've got on your overall system. The other version would be a recovered resource system, and we're seeing quite a lot of these around city edges where you may have very large heat rejection from, example, data centers, industrial processes, or energy from waste plants. Now, this would be a slightly different recovery from an energy from waste plant that you would see in a standard district heating scheme, where you might be taking steam out of a steam turbine. You'd actually be taking heat out of the heat rejection system in the condenser. Now, so you can have very large heat input. These ones are normally for systems where you're more concentrating on the heat supply than on providing the cooling input, but obviously you're providing a service to the people from whom you are taking the heat as well. Just moving on to some of the benefits. So we've talked about pipe work. You don't have to take that heavy, costly stuff at the top there. You can that requires lots of design. It has to think the civil works that go around it have to consider expansion and contraction of the pipe work. You have to do quite a lot of detailed stress calculations. It's quite a complicated thing to put in. Well tried and tested. It's it's certainly effective in what it does. But if you can consider using the more straightforward plastic pipe work, which has much lower civil and infrastructure costs as well as the pipework costs, then that's going to reduce your overall capital expenditure. The heat is likely to be either free from the environment or very low cost from heat recovery. The heat losses in the system are going to be exceptionally low when you compare them with a system which is even the fourth generation systems that we talked about. You might be talking a small fraction of a percentage, and you can possibly, particularly in city centres I've talked about, be sharing heat around an area or around a city centre, even within a group of buildings. You don't need heat metering, so that building interface is much more straightforward for the district heating operator, and it's easier to maintain energy market competition. And so some of the considerations which some of the difficulties we've had with lack of regulation in the heat market is avoided completely. And you still can access Clean Heat Grant or HNET funding. The recent consultation on Clean Heat Grant has made it very clear that you can take the grant for installation of individual heat pumps in properties and use those as part of a shared ground loop, for example. Some of the main issues are that for the building owner, it is a slightly more complicated proposition. You do need the heat pump, and there are some fairly significant risks related to retrofit, as I alluded to. Building systems aren't always designed for these much lower operating temperatures that would be preferred with heat pumps. So there is a consideration here about how you get to modify the internal system. So you're shifting some of the risk towards the building away from the district energy operator. Some of the other kind of commercial issues which we come up across is essentially, what are you comparing it to? What is the counterfactual? It's very difficult for a heat pump to compete with a gas boiler, even if it's being somewhat supported. Apart from anything else, building owners know boilers. They've had to deal with them for years. They know how to cost it. They know what they're likely to be in for. And so it's quite tricky with this system to compare like for like. It's certainly possible, but you do have to go through quite an extensive conversation with your customer to figure out how to demonstrate the value. So fixed charges are likely to be high, but the variable costs will definitely be lower. Okay, I hope that's been helpful, and I will now pass over to the next presenter.
Sorry, Tom, I think your mic might be muted.
Hello?
There you go, that's better. Yeah.
Hello. Okay, thanks, Bruce. Right, so my name's Tom Norton. I'm associate at Fairheat. I've been in the industry for about 15 years. Started off looking more at energy master planning and looking at planning large networks in London. 5 years ago, co-founded Fairheat, which is a company whose sort of mission is looking at getting building level heat networks working, particularly for residents. Started off doing a lot of reviews of new designs, But over time within Fairheat, I've been focusing on heading up the operation side, so looking at how to improve existing heat networks. So as a company, we've seen sort of everything from the very beginnings, from energy strategies all the way through to a lot of operational data of existing systems. So we've kind of seen the whole broad spectrum of how heat networks work. On a personal level, within Fairheat, also co-wrote the CIBSE HIU test, which is now become sort of the industry standard for evaluating the performance of HIUs, and also created acceptance testing, which is a tool used to help ensure that heat networks are actually commissioned correctly all the way from the residents' experience, so that on day one when they move in, the heat networks works as it should do. So as I said, at Fairheat we focus on the communal building side of heat networks. So today I kind of wanted to focus on the considerations for 4th and 5th generation communal heat networks. So just I'd like to open with some questions. So what are 4th and 5th generation heat networks? Then looking at what heat generating technologies can be used with each approach. When should a 5th generation heat network be considered? Which system has the high heat losses, and which approach is better? And again, just to reiterate, this is about working within the communal sort of heating system within a building. So I just wanted to show, so Bruce started by kind of defining what he felt sort of 5th generation, 4th, 5th generation is. I wanted to bring it back just quickly so the image on the right is actually where 4th generation district heating was first mentioned by Professor Lund, a Danish professor, in 2014. And he defined 4th generation as any system with flow temperature under 60 degrees, technology agnostic, easy to integrate new technologies, ability to use waste heat, ability to store excess heat. So for me, that kind of covers a lot of what we're talking about as well with ambient systems. So for me, it's 4th and 5th generation is a bit of a grey area in that there's no clear definition of when 4th and 5th generation actually sort of separate into different technologies. So for me, for the purposes of the presentation and sort of purposes for everyday work, I define 4th and 5th generation as follows, really. So 5th generation is where you need localized temperature boosting to serve end user requirements. What that means in communal systems is that you're usually limited by the hot water temperature. So you can get space heating systems, you can get your underfloor heating systems down to low temperatures, but you'll always be limited by an absolute minimum of about 45 degrees domestic hot water. That means on the image on the bottom, that means that on your plate heat exchanger, you need to provide heat on the primary side of 50 degrees to ensure that you can get 45 degrees out for the resident to use. So another way of presenting that is anything above 50 degrees primary flow temperature is what I'd consider 4th generation, and anything below primary flow temperature of 50 degrees I'd consider as 5th generation. These also have different definitions on the continent. In Scandinavia, below 50 degrees is sometimes called ultra low temperature district heating, and above 50 degrees is just low temperature district heating. And just to reiterate that concept, that anything below 50 degrees requires domestic hot water boosting, and anything above 50 degrees doesn't require any additional temperature boosting. So I also wanted to quickly cover some common misconceptions that I hear about 4th and 5th generation. So both 4th and 5th generation within communal heating systems use the same heat generation sources. They can use heat pumps, air source, ground source, water source heat pumps. Both technologies can use CHP, whether gas, biomass, boilers, gas boilers, electric boilers, utilize waste heat sources, biomass, and also, which will probably become more important in the future, they can also utilize, both types of systems can utilize other district heating sources, and that includes 5th generation district heating. The other misconception I hear is that the term 5th generation implies that it's better fundamentally than fourth generation, as it's just an evolution from fourth generation. That's not the case. They're effectively two different approaches and can actually be complementary to each other. What I mean by complementary is so similar to what Bruce was discussing about on a city level or even within a group of buildings. There can be a network, an ambient loop or a fifth generation network as like a main ring main or a main network, and then you can have fourth generation systems tapping off of that with heat pumps in the basement to boost within the communal system. I can also take waste heat sources and also if you have data centers, energy from waste, things like that, those can also feed into that fifth generation ambient loop. So that's how I define fourth and fifth generation. So just quickly what I mean by communal heating system. I think it's probably quite clear, but just to ensure we're I'm clear in what I'm defining those are. District heating is multiple buildings. Communal heating is the heat network within a single building. So I would consider this kind of setup as the district heating element would be the energy centre and then all the distribution pipe work, and then the communal is all the heat network that is going on within the building. So in summary, so fourth and fifth generation heat networks in communal heating systems. So fourth generation are typically individual HIUs, heat interface units in each dwelling, generating instantaneous hot water served from a central plant room with a low temperature heat network. And fifth generation would be individual heat pumps in each dwelling with stored hot water in each dwelling, served by central plant with an ultra low temperature heat network. So both of these concepts have central plant rooms and they both have heat networks. The key difference is fourth generation, you have an HIU generating instantaneous hot water, whereas a fifth generation, you'll have a secondary heat pump, which will be typically storing water in a hot water cylinder within the dwelling. So a kind of pictorial representation of that is, so this would be a fourth generation system. So you have the central plant, which could have heat pump, boilers, district heating, distributing at about 50 to 60 degrees into the buildings with HIUs, and then returning at 20 to 30 degrees. And each flat would have a HIU, would be generating hot water instantaneously. And then for a fifth generation system within a building, it would be again the same central plant, heat pump, boilers, district heating, generating the heat, and then that would be being boosted up to the required temperature within the dwelling, and then the hot water would be stored in a cylinder within the dwelling. So from an engineering perspective, when I look at them, I kind of have these risk items that I'd like to sort of review. So capital costs of the systems, the operational costs, and they're made up of a lot of factors. So the utility costs of what you're paying for your electricity centrally or in the dwelling, or any other utility costs, could be gas. Maintenance, both within the central plant and within the dwelling. Thermal storage, size and ability to use it to react to price and carbon changes. Heat losses from both systems, pumping energy, and plant efficiency. So what choice of centralized plant you have and what ability you have to upgrade it in the future. Some other non-cost risk items would be operational data. So do you actually have performance data of how these systems work in reality? What industry sort of skills there are around commissioning and maintaining these systems? What are the spatial impacts of both systems, and refrigerant use, and with the banning of sort of a lot of current refrigerants in the near future and moving towards refrigerants with low global warming potentials, how that impacts their performance, and also noise of the systems. So quick comparison. So this would be, again, so this would be within a communal heating system, where you're looking at particularly heat. The capital costs would tend to be higher for a fifth generation system. Well, a fifth generation system, it would be higher if it was heat only. If you have a very good balance of heating and cooling, then they're closer in cost because of the ability to share heating and cooling. And you only need one plant instead of doubling up with heating and cooling plant. The utility costs for fourth generation systems tend to be much lower because you have the ability to buy in bulk, particularly if it's an organisation that operates several heat networks, and they can take advantage of even greater purchasing power for utility prices. Whereas in fifth generation, there's a lot more onus on residents paying for electricity at a much higher cost. Central plant maintenance tends to be the same with both systems. They, as I said before, they can have exactly the same central plant technology. The dwelling plant maintenance is far higher in fifth generation for two factors. One, you have heat pumps, which are much higher maintenance than an HIU, but also you have unvented domestic hot water cylinders. So you're going to need at least an annual maintenance check within dwellings. Heat loss, I would say they were both low. I'll come on to why I'm not really differentiating between those two of them. Commissioning and maintenance skills, I'd say there's much more developed skills around fourth generation, around HIUs than there are around heat pumps. And similarly, the impact on supply chain. So at the moment, we're selling about 30,000 heat pumps within the UK market. So the impact of putting heat pumps into many more dwellings will create quite a large strain on the supply chain. And the ability to share heating and cooling between users, so as Bruce alluded to, that's a particular benefit of fifth generation. You can share heating and cooling between dwellings. And operational data, so there's operational data available. So fourth generation systems, there's quite a lot of data available. Fifth generation is quite new, there's a lot less data, so it's much harder to evaluate their actual their performance in use. So just going into two or three of those in a little bit more detail. So heat loss. So for fourth generation systems, so these numbers are in watts per dwelling, instantaneous heat loss, watts per dwelling. So we typically see for a well-designed, good performing fourth generation heat network, we would tend to have about 45 watts per dwelling in the network, and about 25 watts per dwelling within the HIU. The 25 watts can be reduced if you do some clever things with standby modes and keeping temperatures warm away from the dwellings. But as a general approach, this is fairly standard. So you're looking about 70 watts per dwelling of heat loss. If we look at fifth generation heat loss, again, this is within the communal systems. You've got network, so there will be some heat loss, but it will be marginal. So just for the sake of argument, I'd say there's zero heat loss from your network. Because you're storing water in your hot water cylinder within a flat, you typically have about 65 for about 170 litre hot water cylinder, modern hot water cylinder, you'd have about 65 watts. So there's actually not a significant difference really between, when you look at the network and the dwelling heat losses in total, there's not a significant difference in heat losses between the two approaches, and that's down to the fact that you don't have to store hot water in a fourth generation system. So operational data, so this is some data from one of the sites that I've worked on. So this kind of demonstrates that effectively fourth generation is being implemented in practice and works, and we have lots of data. So this is an example of a system with the blue line at the top showing the flow temperature and the green line showing the return temperature. So this is over about half a day in January this year. And we have a flow temperature around about 55 to 60 degrees and a return temperature around about 30 to 35, and occasionally dropping down to the low 20 degrees. So when would we use fifth generation heating, district heating? So within buildings, so I have a couple of quotes, a couple of sources. So there's one that's a rough metric that you need. That fifth generation district heating could be appropriate if there's more than 40% of the load must be cooling. Also, Phil Jones from the Building Energy Solutions suggests it's the figure around about sort of 50%. So if your 50% of your total load is cooling, then fifth generation could then be a viable technology. But I'd make the point that in communal heat network, heating, domestic hot water and space heating usually dominate significantly in the total load of the systems, and it's very uncommon that you see 50% of cooling. Where that can be in communal systems is, for example, if you'd have a development that's a mixed use and you could be connected to a supermarket or something, and you have a contractual, a very tight contractual arrangement with the supermarket where they have high cooling loads, and you could potentially share those cooling and heating loads between supermarket and the residential properties. So a quick summary of the pros of fourth generation communal heating. So typically lower capital cost. If cooling isn't the dominant load, then it typically is a lower heat cost as well for residents, typically due to the lower utility costs. It's a more mature market, there's less skill shortage and strain on the supply chain. There's no dwelling hot water storage cylinder heat losses. There's an ability to use more efficient and larger heat pumps centrally and upgrade them over time instead of them being installed in each individual dwelling. There's much less in-dwelling maintenance required, which can be a very costly element of operating a heat network, getting access into dwellings. There's less space use within the dwellings. There's no issues with refrigerant use within the dwellings, and it's a proven model that works and with data to back it up. Fifth generation in communal heat networks, the pros would be obviously if you have allow sharing and heating of cooling within the building. So if cooling is a dominant load within the building, if it's a mixed use scheme and you have a high cooling load, then it can be cost competitive. You have lower distribution losses around the network, and it'll tend to have a smaller central plant area because you're shifting some of the heat generation into each individual dwelling. So just to go back to just my final few slides, so just go back to the opening question. So what are fourth and fifth generation heat networks? So to me, there's no standard definition, but I would use that fifth generation heat networks typically require localized temperature boosting for the end user's requirements. What heat generating technologies can be used with each approach? So the same heat generation technologies can be used. I commonly hear one approach is that fourth generation is gas boilers, gas CHPs, and that's not the case. Fourth generation systems work perfectly well on heat pumps and electric boilers. And when should a fifth generation communal heat network be considered? So typically it's around about 40 to 50% of the total load should be cooling for it to be a cost competitive. Which system has the higher heat losses? So if you take into account the network losses and losses within the dwellings, then they typically have similar heat losses. And finally, which approach is better? So as I said at the beginning, the term fifth generation can imply that it's better than fourth generation, but that's just terminology. And in fact, that's not particularly the case, and each individual fourth and fifth generation is applicable to different situations, and that should be reviewed specifically for the application. But it's important to note they are actually complementary technologies and can be used together. Okay, thank you. That's all from me. Over to you, Chris.
Hi all, I hope everybody can hear me and can see my presentation. So my name's Chris Davidson. I've been designing fifth generation and fourth generation networks since before either of them were defined. I've been doing it for about 20 years now. And what I'm going to do is take you through what available technologies we have and also look into implementation and optimization of systems. And I'll finish up with some real world case studies that are actually in and installed, and one of them at least has been for 10 years now. Thanks so much for your questions so far. Nikos has asked me to point out if those in the audience could like the questions that they would mirror themselves, then we can make sure we'll prioritize those at the end of the presentations. So available technologies. Higher generation heat networks, so fourth and fifth generation heat networks, allow a far wider range of heat input options than conventional equipment, and that's simply because, or conventional networks, and that's simply because we are running at a much lower temperature and therefore can accept heat, which will naturally flow from a hot place to a colder place from more sources. So any very low temperature resource is available to us. So that could be cooling in a building, refrigeration, as has already been mentioned. It also allows us to use more intermittent temperature resources. So they may be higher temperature, but running intermittently. And because the way the networks work, we can actually smooth those bumps out in the road and make more utilization of those high temperature resources. As the previous two speakers have already mentioned, we can use air source heat pumps, we can use ground source heat pumps and water source heat pumps as a source for these networks. And what I'd like to do for the rest of my presentation is concentrate on my specialist subject, which is ground source heat pumps, in a little bit more detail. And the reason I'd like to talk about that is just that's because I know what because I'll be knowing what I'm talking about, but it's also because it does have a unique advantage, a ground source network, in that it is really the only large scale opportunity we have for true interseasonal energy storage. And as Tom has already mentioned, hybrids are not just allowed, they are encouraged. Hybrids of these systems can be very, very effective, utilising different sources, different loads, and different storage mechanisms such as ground source. Implementation, even in the densest of city environments, is possible. There's a lot of myths around ground source in particular that you can't do it in city centres. Well, this project here is a city centre project in Oxford. It's for the Earth Sciences building at Oxford University. I designed it about 12 years ago. And as you can see, these folks and ladies are installing pipes in a basement which has been dug out to a storey below ground level. Lots of trades involved in this, so the secant walls have been installed, a drill rig was lowered into the basement working alongside pilers. So particularly in city centre locations, there are practicalities and coordination issues which are key, but it absolutely can be done. One of the key elements and one of the really key takeaway messages I'd like for everybody in the audience is it's really important to get specialist design advice early on in this type of project. Many engineers can get themselves in a real pickle or just write projects off when otherwise they're actually perfectly viable projects by doing a literature review sitting in the desktop. So getting skilled and experienced design advice is very important at an early stage of the project. And also, as the project develops, skilled and experienced contractors are also essential. So the key message there is that the solutions are bespoke and they can scale to meet practically any loads, even in the densest city centres, but it's really worthwhile getting that specialist advice in at an early stage, even at feasibility study. Optimisation is all important in doing ground source design, and I've been just keeping an eye on some of the questions coming in. A lot of them have been asking about what does this resource look like and how do we model it? Well, actually, the modelling of ground loop systems is very well advanced. The original equations were written down in 1946, and the first software models were developed in the 1970s. That was actually during the first oil crisis, when ground source was seen as a real opportunity for the future. It's true to say, though, that the better the information into the models, the better the information out. And to answer some of the questions that have been coming in the chat, we really need very detailed building models or monitor data to be really certain about what the ground interaction needs to look like to make it sustainable in the long term. And this is an example on the top here of a graph of an hourly model running over 10 years for a real building. And this on the bottom is the ground temperature plot that results from a sustainable ground loop attached to that building over 10 years. And this is what I spend most of my days doing. I know the cold winter nights just fly by. One of the key messages also on this slide is commissioning, control and monitoring are critically important to the success of these systems. A proper commissioning regime must be in place, and ideally that should extend at least 18 months into the lifespan of the building so that the systems can be properly optimized. And I'm going to talk in a second about projects that are very complex and have lots of levers to pull, and all of those levers need to be put in the right position before we can truly say that that system is fully commissioned. When I'm doing this face-to-face, I'd normally be looking for audience interaction, so I'm hoping that you're all enjoying what's being said and are interested in what's being said. I'll have to take it as read until we get to the questions at the end. Okay, so finally from me, just a couple of case studies. So these aren't new systems. This building, spectacular building in London, when the lockdown's over, if you are in London, that roof terrace is a wonderful place to have a glass of something on a summer's evening. It's over 10 years old now, so we're not talking about research and development projects here. We're talking about real implemented technologies that have been installed, not just in the UK, but around the world for years. This is one new change. It's owned and operated by Lion Securities and consists of 4 levels of shops and restaurants with 4 levels of office above, and as I said, a nice restaurant and rooftop bar on the top. That's the view down on the building from the dome of St Paul's Cathedral, if you want to get your bearings. It's about 3 megawatts of heating and cooling. So there's 3 megawatts of heating and 3 megawatts of cooling. And there are thermally active foundations, so closed loops in the foundations of the building, coupled with water wells taking water from the chalk at about 80 meters down, using that water to either reject or extract heat from the ground and then putting it back into the ground again. One of the things I always try and get across to people is that we in the UK tend to think of ourselves as somewhat behind the rest of the world. This project is cutting edge and is actually more advanced than virtually anything that's going on anywhere else in the world, because of the modes of operation, but the different coupled systems, and because of the mix of systems. If it were a number of buildings, it would perhaps be 20 buildings, but it's in city centre London, so it's 1 building. So this is really a district central plant ground source system that's doing all of what Tom's talked about in the 4th and the 5th generation. The mix of loads in there range from refrigeration in a supermarket to heating and cooling the offices and heating and cooling the shops. The second case study I wanted to talk about is the different architecture, in that this is now a true 5th generation network. It is distributed plant. Every apartment has its own heat pump, has its own hot water cylinder, and are fed from a loop at ground temperatures, which is feeding 8 blocks of apartments in North London. Each block has 64 apartments, so 64 heat pumps, and affordability and fuel poverty reduction are core to the business case in this instance. The loops extend to 240 metres below ground level, and each dwelling has a heat pump from Kenza, the heat pump company based down in Cornwall, which does 100% of the heating and the domestic hot water for the property. One of the gratifying things, having designed this project a couple of years ago now, is that it is delivering exceptional levels of tenant satisfaction, which I think is testament to the maturity of the technology and the project team that installed it and implemented it. So I'd like to just say thank you, and I'd like to hand over to questions.
Hi. So we can read out loud some of the questions, and so some of them have been, most of them I would say have been asked out loud, and but the most liked ones we can actually ask them So one interesting question was how are we going to deal with Legionella as a fifth generation district heating runs at low temperature? Who would like? So Chris, would you like to talk
sure.
further about it? Yes.
So the network itself is dosed and sealed, so we don't have any concerns with Legionella in that part of the system. But you do need a Legionella strategy within the building then to ensure that particularly the domestic hot water is treated appropriately. There are a number of different strategies that are applicable. So for example, the most common with distributed heat pumps is to have an immersion heater in the storage cylinder, which does a pasteurization cycle at regular intervals. But there are a number of different options.
Thank you.
Yeah, I would, Anikos, I would, on the communal heating side, I mean, Chris kind of hit the nail on the head, really. So yeah, there has to be, typically you'll be delivering at 55. So you need to be storing at 60 or at least elevating that storage temperature to 60 degrees fairly regularly to ensure pasteurization. So you have to, when you're evaluating the technology, you have to make sure that you are considering that as an additional energy use into the system.
Thank you, Tom. Another question from the speakers: how would an ambient network operator de-risk reliance on a single energy source, for example, a large data center? Bruce, do you want to?
Yeah, sure. I think that's a really good point. It is very tempting to see a massive energy source and think, oh well, that'll always be there. You have to say that quite a lot of this big infrastructure, for example, data centers and waste treatment plants and so on, are pretty long-term investments, and people don't turn them off and walk away on a regular basis. But it's absolutely right to say that you need to make sure that you have a development plan for your network which takes resilience into account, does some resilience planning. Now that could be either it could be having something in place to replace the source of energy, but equally it's about looking for other places to balance your load across the network. As has been mentioned a few times, these things are better if you've got more cooling coming into the system as well as heating going out. But you might also be looking for alternative sources across time. So you could have a plan in place for how you replace that should it go. So normally your first port of call is to make sure you have a contract with your potential heat source to ensure that you have suitable notice and that you don't suddenly lose that energy with no notice. But backup and backup supplies in the development plan are incredibly important.
From a sorry, Nikos, from a sort of smaller scale system, that is always difficult. Particularly, these decisions are made planning or pre-planning. So even so, I used an example of potentially that you might have a mixed use development with a supermarket or something that is rejecting a lot of heat. It's very difficult to get those organisations to commit contractually to supplying that cooling, regardless of the financial benefit, no matter how clear you make that financial benefit will be to them. Sometimes they have very much one size fits all, and so it's very difficult to get them to commit to a contract at that early stage.
Since you're third, Tom, there is a question: if the heat losses from a fourth generation are low, why BRE has increased the DLF default values in sub 10? I think you already answered, but maybe you want to say out loud.
Probably my first comment would be you'd have to ask BRE that.
Yeah.
So from our experience, the DLF values in SAP10 are not representative of the heat networks that I work on and we see. I think I mentioned historically, I think with all these new technologies, fourth generation or district heating or communal heating in itself is only had a rebirth sort of in about 10 to 15 years ago, and that's been a learning curve, and I don't think anyone involved in the industry would pretend that it hasn't been a very steep learning curve for district heating. So there are older systems that aren't performing very well, and I think they may be overrepresented in the SAP 10 figures, but it's now kind of much more of a mature technology with much greater supply chain and skills. I would say, linked to that as well, you have to consider that now there are new technologies entering the market, and you should probably exercise the same amount of caution on the old performance of fourth generation systems as you might do on some of the new technologies, because at the moment a lot of decisions and claims are made on theoretical figures, and as I showed, there's lots of data out there, and we have data of how these systems perform, and through no fault of their own, new systems obviously do not have that weight of data to back up the claims at the moment.
Thank you. There has been one question with a lot of conversation around what regulations and controls are there typically put in place to monitor the temperatures in fifth generation district heating systems and make sure temperatures are staying in range that are of use of the buildings connected? How do you prevent buildings taking or injecting too much energy?
Do you want me to take that one, Nikos?
Yes.
So the design of particularly a ground source fifth generation network relies on designing in a capacity to that ground loop to be able to meet the building loads sustainably in the long term. And that's one of the points I was trying to get across in the presentation, is that we need a far better degree of modelling or monitoring data to accurately model ground loops than is traditional. So we can't just buy more gas. We are installing a finite resource in the ground. So actually, this is one of the big challenges for the industry to get their heads around, is that the level of capability in terms of modelling that heating and cooling loads needs to go up across the piece. So we can build in contingencies, and we can build in opportunities to expand networks as load profiles change, but fundamentally, from a ground source point of view, that ground loop is a finite resource that needs to be designed and installed.
Yeah, I think just from me, in terms of the commercial arrangements, all heat networks need to have monitoring of them to verify performance. I think 5G networks typically can operate effectively across probably a wider band range of temperature variation than you might like to see on a fourth generation or earlier network. By that I mean the heat pump's quite happy working across a sort of a 10-15 degree range, depending on what sort of pump you've got installed. But so you've got a bit more variation potential available within the network. So the larger the network you have, the more resilient you are just through inertia. But every contract would have a monitoring arrangement and a set of KPIs and performance standards with some arrangements for compensation if there are issues that go outside on either side of the fence, i.e. the operators not maintaining their side of the bargain, or the buildings going outside its performance parameters that it's paid for. So you would expect there to be some kind of commercial arrangement in there, and it's a case of just monitoring temperatures and flows to ensure they stay within the design margins. But as it's been said, getting the design right and making sure you've properly modelled your buildings up front is a really key part of sizing all of this.
And picking up from the other side, is there any advice to install backup systems in the event that the temperatures become unfavorable for any period of time and that the building would not be able to reject any heat?
There are options, Nikos, to use auxiliary equipment on closed ground loops. It's very common to use dry air coolers to reject excess heat, particularly running those dry air coolers at night when the efficiency of the dry air cooler itself is far higher. So there are options out there. Most people who model these things are capable of taking account of those hybrids. So and that might be part of the original design, but then moving on to if there's a problem down the line, then the same approach can be taken.
Yeah, I think it's worth saying that there's a fair degree of variability in all of these because of the different types of systems that you can have. This is certainly not a one size fits all. So if you're taking or rejecting heat to the sea, you are, to all extents and purposes, using a nearly infinite resource. For the purposes of the sort of system we're looking at here. Whereas, as you say, if you're going to a ground loop, you have to design that and build it to suit the loads that you're dealing with. So all of these things are very dependent. So the answers that we're giving probably are highly variable, but we're trying to give you a guide as to the sorts of directions you ought to be thinking in.
Yes, and there is a question from Marius regarding the recommendation that from a guidance draft on April 2020, there is on point 9 that the GLA do not support 5th generation district heating in H&E PAs. What's your view on this?
I'm staying silent because I don't. I'm not aware of that.
Or in general, what's the support from the government for 5th generation district heating projects?
Yeah, so I did just touch on that on one of my slides. There is a range of different options. I think it's fair to say that the policy and support landscape is in a state of flux at the moment. So various different mechanisms have been available, and probably there will be others coming forward. Historically, you have been able to attract RHI for a ground loop network, for example. There has been some suggestion that you might be able to use the industrial heat recovery project, heat recovery grant structure for some of the heat recovery from processes. We're now getting indications from the way in which the recent clean heat and the future of RHI documents have come out in the last few days, indicating that they're more likely to go for capital infrastructure support. So this is likely to see the heat networks infrastructure program and the follow-on clean heat networks project, which was trailed in the budget, being the key route to government support. That's effectively a finance gap arrangement. So you put forward a model and you say what your investment return is needed. If the model shows that you don't quite meet that, then the government will provide a grant to cover the gap, subject to state aid rules. There was an indication that for example, for a shared loop project, if you were dealing with individual householders or small businesses under 45 kilowatts, then I think they're promulgating a £4,000 per heat pump grant support. So it'll be interesting to see how that consultation comes out. No doubt there'll be a bit of a tussle. One of the tricky things about all of these programs is that they put lots of them out there. They all interfere with each other in one way, shape or form, and it becomes quite a minefield trying to pick your way through how to get the best support for your system. So yes, it's a changing landscape, but those are the key ones at the moment.
Thank you.
I think I don't really know the background, to be honest, on the GLA's policy statement, but from I mean, it could be that it's in reaction to the number of applications that are coming through for ambient technologies, and this may again reflect back to that they are new technology, and there may just be some concern, which I think probably is sensible, or maybe less concern, but a cautious approach to make sure that there isn't suddenly a sea change in that a policy decision may has caused a complete sea change in the technology that people are specifying, and that they need to be a bit more careful about ensuring that people still correctly appraise the developments and weigh up the risks.
One point I'd like to make to build on that is that I participated over the last few weeks in a consultation about the heat pump supply chain and its capability to deliver. A BEIS report will be published in the next few days, and it shows that there's no capacity constraints evident.
And since you're up, Chris, I think this one for you, like on the efficiency of the 5th generation district heating systems. Has there been done any study to identify the increased efficiency of having a lower temperatures?
Yeah, there have been a number of studies done on existing buildings, many of which I've been involved in the design and installation of. There's quite a lot of case studies out there. Would I like more data? Of course I would. And it's very often the case that whilst everybody wants to monitor everything, nobody wants to pay for that. So it has certainly reduced the amount of data that we could have had. If I had my last 20 years again, it would be one of the key things I'd be trying to do is get some government funding in to monitor more of the particularly larger scale installations. But there is information out there, both in a UK and a global scale. Before I left my contracting company in 2013, we had about 20 monitored large-scale buildings in place, and that company's continued to publish the data on it.
Thank you. Another question, what would motivate someone to reject heat into a loop at, let's say, 30 degrees if they could more easily just reject it in the air at 15 degrees? What would be motivation for end users for?
Do you want me to take that, Nicholas? Well, there's two motivations. First of all, water is a far better conductor of thermal energy than air is. So that's one motivation. And the second motivation is that whilst the air is at 15 degrees, you will generally need to heat your medium up higher than that, up towards the 20 to 30 degrees, in order to reject heat to it in an efficient way.
I think it's also worth mentioning that most developers, particularly in dense city centre areas, are desperate to get rid of heat rejection systems on their roofs. They can make much better commercial use of that space for equipment for customers, data connection points from satellite and that sort of thing, than sticking radiators up there, which cause them problems in noise and weight and loading on the building. So there's a number of different incentives for the operator. Not the least of which is the loop is likely to operate at a more stable temperature, and so when they're wanting to reject most heat, the temperature they'll be rejecting at will be considerably lower than the 28 or 30 degree air and the higher air temperature the higher water temperature that needs to go with that.
Thank you. And there is an interesting question saying that is it possible to have a 4th generation system where the customers are actually using a heat pump to draw heat from their return pipe and have such a 5th generation district heating, which the return pipe might be below 50 degrees, and then just draw the energy from there and recirculate it to some houses that they might be passive houses, for example, and could support a 5th generation with low temperatures. What's your view on that? Have you ever?
I've not seen one, but we have considered it. We looked at a strategy for expansion of district energy in Exeter a year or so ago, and we looked very carefully at the potential for expanding into less dense areas of housing by using the return as a water source for individual heat pumps. Effectively, it ran into some commercial problems, mostly related to the cost of trying to get the infrastructure into the properties. So I think in theory it's a good idea, and in fact we are looking at this for another large-scale network which is looking to expand in order to try and enhance capacity across the system by reducing temperatures. But I'm not aware of one that's been done, but I can see that there may be some benefits for it, for both the 4th gen network and also for providing a heat source into new build developments in particular. So I think that if it's going to happen, that's probably where it will happen, just because of the cost benefit issue. But you know, watch this space. If we manage to make it work, I'm sure we'll be wanting to come out and tell everyone about it.
Well, one little comment on that, if I may, Nikos. We've just got to be very careful in our heat pump selection when we're sourcing off of a very high temperature network, such as 30 degrees, because most heat pumps, or many heat pumps, depending on the refrigerant and architecture, will find that pushes them up above their high pressure limits.
Yeah, so I think that's a really good point. We've been told by more than one small-scale domestic heat pump manufacturer that they don't want water warmer than about 18 degrees. Thank you very much. So please keep your nasty hot water away from us. Yeah. It's less of an issue for larger heat pumps. So it may be that what we end up doing is actually putting a larger scale heat pump in to put a 4th gen network on downstream, but that would enhance transmission capacity to enable us to get more heat to the start of that network. We did look at that before, and it isn't an obvious answer in terms of overall cost, but I can see circumstances where it might be beneficial.
The most common R410A heat pumps in the marketplace at the moment will be looking at 25 degrees entering water temperature maximum.
Yeah. We've in fact, one of the systems we're designing at the moment is one where we've had to look at doing a local cluster for exactly that reason. So we've effectively taken a wide area 5G network and done a local 4G network in order to allow us to use a larger heat pump using ammonia rather than some of these other refrigerants, and that does allow you to use the higher temperatures.
Again, it goes back to the point, Bruce, that hybridizing these networks is actually very easy, but it needs thought and needs to be done carefully.
Absolutely.
And another question is on the technical side. If on a 5th generation district heating, there is a much lower differential temperature, and the 5th, for example, 5 degrees, and then on 4th generation there is a 30 degrees. Do we not need to circulate 6 times as much water, and how does this affect the practical side of the installation?
Do you want me to deal with that, Nikos?
Yes, go ahead.
So the flow regimes in high temperature and low temperature networks are very, very different, and that is part of the consideration. So I probably spend 40% of my time on a design not working at how much pipe needs to go in the ground to do the collection, but what that network on the surface needs to look like. So one thing that we do an awful lot of, for example, is rather than treating those blocks of flats in Enfield that I talked about earlier on, rather than treating each block as a single block, we treated it as individual risers on that block, which kept the pipe sizing down, but kept the flow rates up high enough to keep the heat pumps happy and to keep the pumping costs down. In actual fact, on that system, there are no central pumps. All the pumping is done within the heat pumps itself. We're using tiny little pumps. So we need to actually maintain a sensible pipe sizing. But bear in mind, of course, that it's uninsulated pipe in most instances. So there's a massive cost impact there. So yes, it is a very different flow regime between the low delta T, low temperature networks and the higher delta T, higher temperature networks. And the philosophy of how you design them is naturally very different as a result.
Yeah, I just I don't think I sort of commented on that. So yes, I mean that is one on a communal system level. That is definitely one impact. So we're looking at much higher flow rates in the system. So pipes need to be much bigger. But as Chris mentioned, it's insulation typically needs to be lower. So there's a bit of give and take on that. The water is actually also more viscous at the lower temperatures as well. So that is some more sort of pump energy related to that. And one of the biggest impacts, though, is use of thermal store. So having a centralized thermal store, if you're working on such a low delta T, you effectively have much lower capacity, heat capacity for a given volume. And one benefit of having that bigger delta T and that ability to store thermal energy is that, particularly as we move forwards to variable electricity costs and variable carbon intensity of electricity, it means that the larger the scale you get, the more you can make a benefit of reacting to those price changes and carbon changes. So it'll be easier to do that at a larger scale, more centrally, and the delta T will give you a bigger sort of thermal storage and more to play with.
Thank you. And I think I have one question back to you, Chris. How do you avoid freezing the piles in the building, such as 1 new chains? You've answered, but do you want to elaborate more on this?
Yeah, for the benefit of the group. So we worked in conjunction with the structural engineer, which was ARIP, on that project, to establish a set of design temperature limits on the water inside the pipes, inside the piles, that would allow their structural design to be maintained. We then set that design limit for the closed loop, and when we reach that design limit, we use the water wells to either extract and add heat or reject heat. So we've got an upper limit and a lower limit that we work within as part of the design, and we maintain by using the water wells primarily, but we also have dry air coolers as well. That loop is actually running at between 20 and 25 degrees C pretty much all year round.
Thank you. Just a second. And one more question, one last question actually. Let me pick a nice one. So the cost of Chris asked similar name. The cost of replacement refrigerant is rising rapidly. How popular in dense of urban areas are ammonia-based systems? Who wants to?
Well, just a quickie to say that ammonia is a tricky thing in a dense urban area, and your local environmental health officer will take a very keen interest in what you're going to do with it if there should be some kind of burst in the system. This is not on a heat pump, but in ammonia-based chillers, we've had to do some very significant dispersion modelling to demonstrate that the ammonia can be dispersed safely. I don't know if that was the aim of the question or whether it was just purely on cost, but there are issues with using ammonia-based systems in a dense urban area, and I don't think we would be suggesting that they are put routinely in smaller areas. They need to be thought about quite carefully.
I think it does, Tom here, I think it does highlight though that you do have, I agree with Bruce's concerns, particularly with ammonia in dense urban areas, but I think it does highlight that there's more options. There's one sort of point I was trying to make, that you have more options with a centralized plant. So, I mean, for example, we've been looking at CO2 heat pumps, which can output at higher temperatures and very good COPs, but one of the requirements is very low return temperatures. So it's about if we can get consistently low return temperatures from our 4G systems, which we're beginning to get on a regular basis, then there's options, potential to use some different technologies that maybe only be more kind of applicable at sort of a larger scale.
Yeah, I think that's a really good point. The argument for 5G is not an absolute. It's very much, I think it's been mentioned more than once in a response to a question, horses for courses, and there are times when a lower temperature fourth generation network is far preferable, and being able to use more complex central plant is one of those key ones.
Thank you very much, everyone. Thank you, Bruce, Tom, and Chris, and thanks everyone for the nice questions. I think we could be continuing for the whole evening, but I think we will stop here. And thank you all for joining. And just to mention again that if you're up joining the group, if you can put, I don't know, can you see if you put up the slide? There's on 6th of May our annual meeting. It will be here on Teams, and you can follow us on Twitter. Follow YEPG on Twitter for more details and see upcoming news. Thanks everyone. Once again, thanks Bruce, thanks Tom, and thanks Chris, and Tom and Ryan for being in the back and helping with the questions, and also the technical part of the teams. And hope to see you in the next event.
Thank you, Nikos.
Great stuff. Thank you very much, everyone.
Yes, thank you all for your questions.
Thanks for the questions. Thanks.
Yeah, great questions.